Greetings, everybody. Finding our first example of an area in polar coordinates. And so what we're asked to do is to find the area enclosed by r is equal to 4 minus 8 cosine theta outside of the inner loop. Well, to really get a picture of what this looks like, we should go over to something that can graph this curve for us so we get an idea of exactly what the shape tends to look like. And for that, we'll go over to GeoGebra. Now, for the setup in GeoGebra, remember that we are having our r as a function of theta. And so we will really plot this as a curve, as a parametric curve, where we do something like x of t being r of t times cosine of t, and y of t being r of t times sine of t. And then in this case, for this particular curve, we'll have t going from 0 to 2 pi. So the actual curve that we're going to plot will then be gamma of t equal to a 4 minus 8 cosine t times cosine t for the x function. And then for the y function, we'll have 4 minus 8 cosine t times sine of t. And so the actual command that we'll use to plot this in GeoGebra is going to be the curve function with 4 minus 8 cosine times cosine and 4 minus 8 cosine times sine, with t going from 0 to 2 pi. So this is our actual GeoGebra command. To plot the curve. All right, so let's go over to GeoGebra and see what this curve actually looks like. So what we have in this setup is that the blue curve is actually the image of our function, and the red vector indicates the position vector for the value t on our slider, t going from 0 up to 2 pi. So if we run this animation, we can get an idea of kind of where the inner loop starts and stops, where the outer loop kind of starts and stops. So if we turn our animation on, now we get beginning tracing out the inner loop, and then we move from the inner loop to the outer loop, go through a full cycle for the outer loop, then we come back to the point where our radius is going to be 0, and then we finish with the inner loop. And so now let's see if we can find the values of t for which we only have the inner loop and we only have the outer loop. So if we look for values where our radius r is going to be 0, then we need values for 4 minus 8 cosine of theta equal to 0. Well, that's obviously going to happen when our cosine of theta is going to be 1/2. And so where those values are actually going to happen, if we kind of go back and think about our trig values, then on the unit circle, we know that we're going to have cosine being 1/2 in quadrant 1, but then also by symmetry, we're also going to have a quadrant 4 solution that's going to have the same reference angle. And so for quadrant 1, we can step back and think about our exact value triangles where we had our pi over 6 and pi over 3, 1, 2, root 3. So our cosine was 1/2 is going to be at pi over 3. And so that tells us that our two solutions are going to be a quadrant 1 solution and a quadrant 4 solution with reference angles of pi over 3. And so what we actually have then are values where theta is going to be pi over 3, and theta is going to be theta being 5 pi over 3. So now really from our animation, if we imagine kind of how our domain is then broken up, we have pi over 3 over here and 0 there, our full range there at pi over 2, and then we have 5 pi over 3. So kind of how our domain was broken up, initially we started on the inner loop, and so from 0 to pi over 3, that gives us the inner loop. Then we've got our outer loop running from pi over 3 to 5 pi over 3. And then finally the second half of the inner loop then running from 5 pi over 3 to 2 pi. And so when we want to look for these areas, now we're kind of going to use this as our guide for maybe what our limits of integration need to be in each of these cases. So now, if we actually did an integration of our area, so our integration from 0 to pi over 3 of our 1/2 r squared d theta, what that area is actually going to give us is the area on this lower half of our inner circle. So our inner loop, we get an area that looks something like that. If we then continue the integration, and we then added on the integration from 5 pi over 3 to 2 pi of our area, 1/2 r squared d theta. Now that's going to add on the top part of our inner loop. So we would get an area there. And so what this really gives us then is the area of the inner loop are going to be those two integrals. Now, out here at our kind of midway point through our curve, we have there for theta equal to pi, because we're kind of halfway through our curve parameterization. And so if we would then kind of pick up where we left off, and we looked at the integral from pi over 3 up to pi of our area, so 1/2 r squared d theta, then this is actually going to correspond to the entire top half, so from our radius being 0 out to any particular point on their curve. And so this is really going to give us the area outside the curve. So we'll have this area, but then also from 0 out to the point on the curve, we also capture that inner part of the loop, and we get our area over there in that region. And so our integral from pi over 3 up to pi of 1/2 r squared is then going to capture our entire area here. So that really then by symmetry, if we multiply that by 2, then what this really gives us is the area inside the entire curve. So not necessarily just inside the outer loop, but the area inside the curve total that we would have there. And so also kind of coming back up here, we can kind of see that by symmetry, the red one is going to give us the lower half of the inner loop, and the blue one is then going to give us the upper half of the inner loop. And kind of by symmetry considerations, we can see that these are really going to be equal, that we have a symmetric area top and bottom. And so kind of what we're looking at there is really the area of the inner loop is really then just given by 2 times our integral. We can just do the first one from 0 up to pi over 3 of 1/2 r squared d theta. So our area of the inner loop is given by this. The area inside the entire curve is given by our green integral. And so the area outside the inner loop, but inside the curve, is then just going to be the difference of the area inside the curve minus the area inside the inner loop. And so let's go through and actually calculate those values now with our integration. So our radius was given by 4 minus 8 cosine of theta. And so just doing our integration of 1/2 r squared d theta, we're going to have the integral of 1/2 4 minus 8 cosine of theta squared d theta. Well, if we expand this, what we find is that we have a 1/2 16 minus 64 cosine of theta plus 64 cosine squared of theta, d theta. So what we would then do at that point is to use our power reduction identity on the cosine squared, so that we have our 1/2 16 minus 64 cosine of theta plus 64 times 1/2 plus a 1/2 cosine of 2 theta d theta. So if we clean this up, what we then have is really the integral of 24 minus 32 cosine theta plus 16 cosine 2 theta. Well, that integral is simple enough to do, and what we then have is just our 24 theta. Oops, how about a 24? 24 theta minus a 32 sine theta, and then plus an 8 sine of 2 theta. Okay, and then plus our arbitrary constant. But we're going to use this to evaluate double integrals. And so what we then have is our area for the inner loop. Remember what that was. We said that was going to be our integral, or twice our integral, from 0 to pi over 3 of 1/2 r squared d theta. So we have 2 times our 24 theta minus 32 sine of theta plus 8 sine 2 theta from 0 up to pi over 3. So evaluating this, what we then have is a 2 times an 8 pi minus 32 times the sine of pi over 3. Well, our sine of pi over 3 is going to give us a root 3 over 2 plus 8 sine of 2 pi over 3, and the sine of 2 pi over 3, since 2 pi over 3 is going to be in quadrant 2, sine is still going to be positive, so we end up with another root 3 over 2. If we plug in 0, we have 0 across the board, and so for the area of our inner loop, we're actually going to have 2 times 8 pi minus 12 root 3, or a value of 16 pi minus 24 root 3. So that gives us the area of our inner loop. Then for the entire area contained in the curve, what we then had was equal to 2 times our integral from pi over 3 up to pi of 1/2 r squared. And so what this really then gave us was 2 times our 2 times 24 theta minus 32 sine theta plus 8 sine 2 theta evaluated between pi over 3 and pi. And so what we actually then end up with is 2 times our 24 pi minus sine of pi is going to give us 0. Sine of 2 pi is going to give us 0. So then what we get when we plug in pi over 3, so that we have 24 times pi over 3 minus a minus, which is a plus 32 sine of pi over 3, which will give us a root 3 over 2. And then minus our 8 times the sine of 2 pi over 3. So sine of 2 pi over 3 is then also going to give us another positive root 3 over 2. And so what this then simplifies to is a 16 pi plus a 12 root 3. So then the area that we're actually looking for, so the area between the inner and outer loops is then going to be given by the total area. So we have our 32 pi plus 24 root 3 minus the area of our inner loop, which was our 16 pi minus 24 root 3. And so this gives us an area of 16 pi plus 48 times the square root of 3. So that for a decimal approximation, we would then have 133.4039212. So I hope you've enjoyed this explanation of kind of finding the area between these curves, and I will see you guys in the next example.